Hi there. In today's lecture, we're going to be looking at the new chapter called Taylor series. So a Taylor series is a way to approximate a function by a polynomial. So here we have our function f. Okay, it might be a complicated function. What we want to do is approximate this function, let's say close to this point at x equals 0, via a polynomial. So here we have a second order polynomial p, or a quadratic polynomial, and we see that it approximates the function close to this point. If we have higher order polynomials, so like cubic or fourth order or fifth order, then we will see that we'll get a better approximation to this function. And in the limit of adding more and more terms, this polynomial becomes a Taylor series. And in the limit, the polynomial will then be exactly the same as our function. Okay, now this doesn't always happen. Okay, there's some situations where we can't do this, but for now we're going to be looking at examples that are fairly easy that will allow us to find these polynomial approximations. Okay, so how do we go about finding a polynomial approximation to a function? Okay, so what we want is to have our function f of x approximately equal to some polynomial, which we can write as a0 plus a1x plus a2x squared plus dot 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 plus an x to the n. Okay, so we would like the function to be approximately equal to this finite polynomial. Later on, we will take the limit as n goes to infinity, so we have an infinite polynomial, and then this approximation will then become exact. Okay, but for now, we're going to just look at approximations. So, how can we then solve for these coefficients here? So, we want to find a0, a1, a2, all the way up to an. So, what we can do is first let the function and the polynomial be equal at x equals 0. So, we want f of x to be equal to p of x at x equals 0. That's a good start. Then, to make this approximation even better, we can make the first derivatives equal at x equals 0. So we can have f prime of x be equal to p prime of x at x equals 0. And we can continue this for as many derivatives as we need. And we'll see how that works in a bit. So we can make the second derivatives match, again at x equals 0, and so on. So this can continue for as many as we need. Okay, so this idea of matching derivatives will help match these functions. Okay, so if the functions match at a point and the derivatives match at a point, then the functions should be pretty close to each other. Okay, now how does this help us solve for a0, a1, a2 up to an? So let's go through our list of constraints here, or the list of equalities, and we'll see that that helps us solve for these constants, these coefficients here. So for the first bit, we want the function to match the polynomial. So f of 0 must be equal to the polynomial evaluated at 0, but here everything from a1 and higher will just be 0, because all the x terms will be 0. So we're just left with a0. Okay, so that allows us to solve for a0 quite easily. Okay, what about the first derivatives? So let's calculate f prime. So we have f prime. And then on the other side, we've got our polynomial that we want to match. If we take the derivative, the a0 goes away, and we're left with a1. So it will be a1 plus, then it will be 2a2 times x plus 3a3 times x squared plus dot 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 plus n x to the n minus 1. Okay, that's if we take the first derivative. Now we can substitute x is equal to 0 and see what we get. So if x is equal to 0, everything from a2 and upwards will be 0 if we substitute x is equal to 0, and we're just left with a1. So f prime 0 is equal to a1. So that's how we can calculate this next coefficient. What about a2? Well, we can take the derivative again. So f double prime of x is equal to, the a1 now goes away, and we now get 2a2, okay, the x goes away, so we get 2a2 plus, and now instead of writing this next term as 6a3, I'm going to write it as 3 times 2a3 x plus dot 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 plus n times n minus 1 an x to the n minus 2, because I did the derivative again. Now if we substitute x is equal to 0, everything from a3 onwards will be 0, and we're left with 2a2. So here f double prime over 2, at 0 over 2 is equal to a2. Okay, what about a3? We can take the derivative once more, and we can have f triple prime of x. So the 2a2 now goes away, and we're left with 3 times 2 times a3 plus dot 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 plus n times n minus 1 times n minus 2 an x to the n minus 3. And I hope you see the pattern here. If we substitute x is equal to 0, everything from a4 onwards will be 0, and we're just left with 3 times 2 times a3. So f triple prime at 0 over 3 times 2, and we can write that as 3 times 2 times 1, is equal to a3. And before, we could write it as 2 times 1. Now, if we look at this last term, we see the pattern here. N times n minus 1 times n minus 2. If we continue this, then this will end up being n factorial. Right? Like we had 3 times 2 times 1, that's 3 factorial. 2 times 1, that's 2 factorial. In the previous case, we had 1 factorial, but that's just 1. It's 1 factorial. And even in the case before, we could write this as f naught over naught factorial is equal to a naught. So we have this derivative at the top evaluated at 0 divided by something factorial, and that's equal to our coefficient. So here, if we look at this one, if we wanted to find the second coefficient, we take the second derivative evaluated at 0 divided by 2 factorial, and that gives us a2. For a3, we take the third derivative evaluated at 0 divided by 3 factorial, that gives us a3. So in general, if we want the kth coefficient for our polynomial, we're going to take the kth derivative evaluated at 0 divided by k factorial. That gives us our coefficients for this polynomial. Now, we could do this for a finite polynomial, and we just get a Taylor sum, not a series, because it's a finite number of terms. But we could extend this to have infinitely many terms. And in that case, we would have infinitely many coefficients. So we would need a series of terms. So we can write a Taylor series as a series instead of just a finite polynomial. So we can write f of x is equal to, so it's equal, it's not an approximation anymore, the sum from k equals 0 to infinity. We have infinitely many terms, ak, but that's going to be fk, so the kth derivative evaluated at 0 over k factorial x to the k. So here we have a polynomial with infinitely many terms that if we add all the terms up given a particular x value, we get back our f of x. Okay, now this doesn't happen all the time. Some functions we can't do this, and for other functions the x values might be limited. We will look at that in the next lecture. But for now, we're just going to go through some problems on finding this Taylor series. Okay, the idea of when this can be applied and when this actually converges, we'll save that for later. Okay, so let's look at a first example. Example 1. So for this first example, we have f of x is equal to e to the x. Okay, this is the simplest example that we can look at. So with this one, we see that it doesn't matter how many times we take the derivative, we just get the function back. So here, f double prime is e to the x, f triple prime, and so on, and indeed any kth derivative will just be e to the x. Okay, because the function is its own derivative, so we can do this as many times as we like. We still get back with the function. So what this means is that the kth derivative evaluated at 0 is always going to be 1, which means our coefficients for this Taylor series will be 1 for the top part, that's always 1, and then just over k factorial. So here, e to the x is equal to the sum from k equals 0 to infinity, 1 over k factorial x to the k. Okay, and this is an example of a particular function where this does converge for any value of x. Okay, but again, we will look at that later. But it's good to keep in mind that we can substitute any value of x and this will converge. Okay, something also interesting to notice here is that we can substitute x equals 1 and we get e, which is just Euler's number, is equal to the sum from k equals 0 to infinity, 1 over k factorial, because all of the x terms will be 1. So we can write this as 1 plus, sorry, let's write it out here. So it will be 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus dot dot dot, and so on. So on the right here, we have an infinite series, like we looked at in the previous chapter, and on the left here, we have what it converges to. So it converges to e. So in the previous chapter, we only looked at if the series converges or not, but here we have an example of a series that converges, and we know what it converges to. Okay, converges to e. And we'll see that for particular functions f and their Taylor series, we can choose specific values of x that gives us nice series representations of different constants. So like e, the natural log of 2, and pi, we can represent all of those constants as infinite series. And we'll look at a few more examples later on. Okay, let's look at another example. Example 2. So here we have f of x is equal to cos x. Okay, this is a bit more difficult than the previous one, but not so bad. So the first thing we want to do is evaluate this at 0, and we see that f of 0 is just cos of 0, which is 1. Okay, so that's the 0th derivative, or just leaving the function alone. Now we can calculate f prime. Okay, that's going to be the derivative of cos, that's minus sine. If we evaluate this at 0, we get 0. We can take the second derivative. So the derivative of sine is cosine, but we got the minus, so minus cosine x. The double derivative, that will be minus 1. Now you can find a few more derivatives, but we always have this cycle property of 1, 0, minus 1, 1, 0, minus 1, and so on. So it goes 1 to 0 to minus 1, and then back to 1. And it cycles like this for all of the derivatives. And notice, if it does cycle like this, all of the odd ones will be 0. So all odd terms will vanish. So all odd terms will be 0. Okay? That might seem surprising, but if we look at our function f of x is equal to cos x, we know that cos x is an even function. So if we look at the Taylor series for it, the Taylor series should only have even terms, right? Because if the function's even, the Taylor series will only have even terms. If the function's odd, then the Taylor series will only have odd terms. Okay, so it's not so surprising that all of the odd derivatives are 0. Now all of the even derivatives, so the 0th derivative, the 2nd derivative, and so on, they will alternate between 1 and minus 1. Okay, so how can we use this information to write this as a Taylor series? So we can start with cos x is equal to the sum from k equals 0 to infinity, and now we want to find the kth derivative here. So this first term, or the 0th term, should I say, is equal to 1. And then here, the second derivative, that's going to be minus 1, and so on. So what we can do to capture this alternating behavior is to write it as minus 1 to the k over 2k factorial. Okay, so if we substitute k is equal to 0, in the top part we get a 1, in the bottom part we get a 1, and that's what we get for this, the 0th derivative. If k is equal to 1, then the top part will be a minus 1, and the bottom part will be a 2, right? Because we're looking at the second derivative, and we get this minus 1 part for the top. Okay, so this works out. Okay, and then we're going to have x to the 2k. So here we put the 2k for the factorial and the 2k for the exponent, because we're only looking at the even terms. If we go back here to the top, here we only have x to the k, but this goes over all possible k, even and odd. But now, since it's an even function, we only want to look at even powers of k. Now the easiest way to do that is just to look at 2k. So for any value of k from 0 to infinity, 2k will be even, so this will include all the even terms. So this includes all the even terms. Okay, that being 0, 2, 4, 6, 8, and so on, depending on the choice of k. Alright, let's look at example 3. So here, something a little bit more complicated. F of x is equal to x squared cos x. So whenever you get something like this, where it's a product of two things, try and imagine this as two separate parts. So we've got the x squared part from the beginning bit there, and then we have the cos x part. What we can do is first separate them. We can find the Taylor series for cos, which we did in the previous step, so I'll just write it out. So k equals 0 to infinity, minus 1 to the k, over 2k factorial, x to the 2k. So we know the Taylor series for cos, but here we've got the product of the two. So let's take the product of x squared, not with cos now, but with the Taylor series. So x squared cos x will be equal to x squared times the Taylor series for cos. K equals 0 to infinity, minus 1 to the k, over 2k factorial, x to the 2k. But now the summation is over k, which means x squared is just a constant. So we can take this constant inside the sum. So we now get the sum from k equals 0 to infinity minus 1 to the k over 2k factorial x to the 2k plus 2. The 2 from the x squared gets added on to the 2k from the x to the 2k, and we end up with this. And this is our Taylor series for x squared cos x. So here we didn't have to do any derivatives of f. We just noticed that cos x could be written as a Taylor series. We multiply the x squared on afterwards, and that gives us our result. So whenever you can do a little trick like this to make things easier, you should try that out. Okay, and I'll put a little homework problem. Try out f of x is equal to x sine x. Okay, so very similar to what we did in this previous example. Okay, let's look at example 4. So here we have f of x is equal to the natural log of 1 plus x. Now, you can do this using the method of finding the derivatives and then finding the pattern, like we did with cos. I'm going to leave that as a homework problem. Okay, so find f prime, f double prime, and eventually f the kth derivative. So find that and try to find the Taylor series using that method. I'm going to show you a different method that we can use that's a little bit easier. Okay, so I think it's a little bit easier, but if you want to stick with this other method, that's fine as well. Okay, any method you use, that's perfectly fine. Okay, so for my method, note that the derivative of the natural log is going to be 1 over 1 plus x. Okay, that's if we just take the derivative. So if we keep that in mind, we can write the natural log of 1 plus x as the integral from 0 to x of 1 over 1 plus t dt. So here I'm just using the fundamental theorem of calculus to write the natural log as the integral of its derivative. Okay, so that's just FTC. But notice the inside of the integral, or the integrand, this is the sum of a geometric series. So remember that 1 over 1 minus r, that's 1 plus r squared plus dot dot dot, infinitely many terms. Okay, that's the geometric series where we start at 1 and we have a common ratio of r. But here we have 1 plus t, which means that our ratio is minus t. Just by substitution, we can see that that's correct. So here we can write this as the integral from 0 to x. And then instead of writing this as 1 over 1 plus t, we're going to write it as its infinite series. So we have the sum from k equals 0 to infinity of minus t to the k. Okay, so I've just written this infinite geometric series in the sigma notation form. dt. Now I'm going to swap the integral and the summation. So we have the sum from k equals 0 to infinity of minus 1 to the k. I can factor that out. The integral from 0 to x, t to the k dt. But now this integral is very easy to do. So this is going to be the sum from k equals 0 to infinity minus 1 to the k t to the k plus 1 over k plus 1 from 0 to x. If we substitute 0, we get 0. If we substitute x, we just get x to the k plus 1 over k plus 1. So finally, we can write this as the sum from k equals 0 to infinity minus 1 to the k over k plus 1 x to the k plus 1. So we get our Taylor series without having to do this, all these derivatives, so the f prime, f double prime, and so on. Okay, so this is just an alternative method of finding the Taylor series. So if we can write the function as the integral of something that can be represented by a series, then we can just integrate the series, and that gives us back our function. Okay, but you can use the previous method that we looked at last time. You should get the same result. So try here, just for homework, calculate the Taylor series using the definition we looked at before, and see if you get the same answer as this. Okay, let's have a look at another example that's similar to this one, where we integrate the derivative. So this is example 5. Okay, and we're going to have f of x is equal to arctan of x. Now again, you can use the original definition where you substitute 0, then you find the first derivative at 0, the second derivative at 0, and so on. But here we're going to note that the derivative of arctan is equal to 1 over 1 plus x squared. So that means we can write arctan using FTC as the integral from 0 to x of 1 over 1 plus t squared dt. Again, using FTC. But for our integrand here, we see that it is a geometric series where the ratio is minus t squared. So we can write that as a full geometric series. So that will be the integral from 0 to x, 1 over, the sum from k equals 0 to infinity, minus t squared to the k dt. Okay, we can swap the order of integration and summation, and then take some constants out, so we get the sum from k equals 0 to infinity, minus 1 to the k. Then we can have the integral from 0 to x of t squared to the k, so that's going to be t to the 2k dt. Okay, then we can have the sum from k equals 0 to infinity, minus 1 to the k. Here we can write this as t to the 2k plus 1 over 2k plus 1 from 0 to x. Okay, very similar to what we had before. If we substitute 0, we get 0. If we substitute x, we get x to the 2k plus 1 over 2k plus 1. So finally, we can write the Taylor series as the sum from k equals 0 to infinity, minus 1 to the k over 2k plus 1, x to the 2k plus 1. Okay, so fairly similar procedure to what we did in the previous example. Okay, we're going to do one more example, and then we'll save the rest for our in-person lecture. Okay, so this is example 6. Okay, so here we have f of x is equal to cos of x squared. Okay, so when we looked at the Taylor series for cos of x, that was fairly simple to do. But here we have cos of x squared. That's going to be a bit more difficult to do with regards to those derivatives. So if we take the first derivative, we need to use the chain rule. Then we're going to have to do the chain rule and the product rule. It gets quite messy. So instead of that, what we're going to do is write this as cos of t, where t is equal to x squared. So I've identified my outside function as cos of t, and the inside function t is equal to x squared. This will allow us to find the Taylor series for cos of t, and then just substitute t is equal to x squared. It makes it quite a bit easier to do. So cos of t, we know this one already. That's going to be the sum from k equals 0 to infinity minus 1 to the k over 2k factorial. Here we're going to have t to the k because it's in terms of t. Now we've got this inside function of x squared. So to get from cos of t to cos of x squared, we can just substitute t is equal to x squared. So cos of x squared is going to be the sum from k equals 0 to infinity minus 1 to the k over 2k factorial. And here we're going to put x squared to the k. But if we have x squared to the k, we can distribute the k inside. So this will be the sum from k equals 0 to infinity minus 1 to the k over 2k factorial x to the 2k. Sorry, t to the 2k, that should have been a 2k, so it will be to the 4k. Okay, so here we have t to the 2k, so taking the 2k inside, we end up with a 4k. Okay, so just remember for the cos, it should always be something to the 2k so that it's always even. Like we said before with the even functions having even Taylor series, odd functions having odd Taylor series. So that's a good check just to see if everything's correct. Okay, so here we get the cos of x squared without needing to do any extra work. So we knew what the Taylor series was for cos. All we need to do is substitute x squared, and then that gives us our result here. Okay, so just to summarize. So the first thing, the definition for the Taylor series. So f of x is equal to the sum from k equals 0 to infinity, the kth derivative evaluated at 0 over k factorial x to the k. So this is the Taylor series at x equals 0. If we wanted to find the Taylor series at some other point, then we can just shift all our working over. So let's say we wanted to find f of x expanded out at x equals alpha. So now we can write f of x is equal to the sum from k equals 0 to infinity, the kth derivative not at 0 because we're moving over to x equals alpha, so that will be at alpha, over k factorial, and again we need to shift everything over to alpha, so it will be x minus alpha to the k. So now this will be the Taylor series at x equals alpha. So we just did a bit of shifting there. Okay, but all the work is exactly the same as the previous. So you find your kth derivative, you substitute your point, and then you substitute that into the Taylor series. Okay, number 2, if we have a product of functions, for example, f of x is equal to, let's say, x squared times g of x, what we can do is find the Taylor series for g of x and then multiply the result by x squared. So here we have x squared and then just times the Taylor series for g. So this will be the kth derivative of g. Let's just do this at x equals 0 for simplicity, over k factorial, x to the k. And now we can just multiply in the x squared. Okay, so for our purposes here, we are only going to deal with like x squared or x cubed multiplying inside. You can do the same thing with h of x times g of x, but things get a bit more complicated with that. Because in that case, you're multiplying an infinite series by another infinite series. Okay, it gets a bit messy. So you only need to worry about situations like this. Okay, and lastly, if we have some composition, so f of x is equal to g of h of x, what we can do is find the Taylor series for g of t, and then substitute t is equal to h of x. Okay, so that could be, h of x could be something like x squared, or 2x, or x squared plus 3, anything like that. If we have a composition, we can write this as the sum from k equals 0 to infinity. We find the Taylor series for g at the point, wherever we're interested in. So it will be g, kth derivative, substitute in, actually here, this will be f, kth derivative at 0, again just for simplicity, over k factorial times x to the k. Okay, but here when we have this x to the k, you need to think of this as substituting in my h of x. So this bit over here, we need to substitute that in there. Okay, so this is similar to what we had with the cos of x squared. So g, that would be the cos, so you find your Taylor series for cos, and then substitute your h of x. Okay, so if we think about that, this will be the sum from k equals 0 to infinity. We would have g prime, g, k, oops, sorry, that's a k, kth derivative at, the kth derivative at 0 over k factorial, and then here the x to the k, we substitute the h of x. So it will be h of x to the k. Okay, so this might look a bit complicated, but just think of that example that we did with the cos of x squared. So you find the Taylor series for cos, and then once you've done that, you then substitute your x squared. Okay, so we're going to leave it at that for now. In the in-person lecture, we're going to go through a few more examples, and then we're going to look at where this is applicable. So like I said at the beginning, sometimes you can substitute any value of x and it will be convergent. Other times you are limited to a certain interval where it converges. Okay, we call that the radius of convergence. Okay, so what's the size of that interval on which this Taylor series converges? Okay, outside that interval, the Taylor series does not converge to the function. Okay, but we'll have a look at that in the in-person lecture. Okay, so I'll see you then.